Here we're covering inequalities and graphing inequalities, two variable inequalities. We're eventually going to move on to systems of inequalities, but first we're going to try and come up with an inequality that contains two variables and explain what they talk about, explain what they mean, and graph them. So let's get right into this first problem. All right, Stacy's mom is baking treats for Stacy's birthday party. She has 9 eggs to use for this purpose. A batch of cookies requires 1 egg and a batch of brownies requires 2 eggs. How many of each treat can Stacy's mom bake? So part A lists 3 possible combinations of cookies and brownies Stacy's mom could make for the party. So keep in mind there's 9 eggs in total, and cookies require 1 egg, brownies require 2 eggs. So a possibility is maybe she could make let's see, let's go with 4 brownies and 1 cookie. This is a batch of cookies, batch of brownies, batch of cookies. 4 batches of brownies, 1 of cookies, because brownies require 2 eggs each. So that would be 4 batches of brownies, 2 eggs each would be 8 eggs for that. And then 1 batch of cookies requires 1 egg. So that'd be 1 egg for that. And she has 9 eggs in total. So I've made this count worth 8 eggs, this worth 1 egg. So there's one possibility. Another one could be, I guess, let's say 3 brownies. I'm just going to abbreviate it as B, and 3 cookies. Because 3 brownies, that's 3 times 2 eggs would be 6 eggs. And then 3 cookies, that's 3 times 1 egg, which would be 3 eggs. That's 9 eggs altogether as well. So there's another combination. And then another one would be something like maybe 2 brownies and 5 eggs. Or not 5 eggs, 5 cookies. But 5 cookies requires 5 eggs. So there's just a couple possibilities. Okay. Write an inequality to represent the situation. Okay, so I'm going to use X, if that's okay with you, for cookies. And I'm going to use Y for brownies. So for cookies, 1 egg per batch of cookies. So 1 egg per batch of cookies. I almost wrote C instead, right? So 1X, say 1 egg per cookie or per batch of cookies, plus, now the brownies require 2 eggs, right? So 2Y to represent 2 eggs per batch of brownies is less than or equal to 9 eggs. So this inequality represents the number of eggs used for each dish. Cookies require 1 egg each. Brownies require 2 eggs each. So the cookies plus the brownies, the number of eggs used to make them has to be less than or equal to 9 because we only have 9 eggs in total to make with. All right, so graph the inequality and shade the area where the solutions are. So the first thing that we need to do, what I would recommend doing, is rewrite this inequality in slope-intercept form. So that means just rearranging it, trying to get the y by itself. So notice right now the y value is here on the left side. I've got to find a way to cancel out this 2 and this x as well. If I can get rid of those things, then the y will be by itself. So the first thing we're going to move is the x. Now it's a positive x. It's being added to y. So we are going to subtract x in order to cancel it out, right? X minus x becomes 0 x's. So that's going to disappear, but we're going to have to move it over to the other side, the right-hand side. So this leaves us with 2y less than or equal to 9 minus x. You can write it like that, or you can write negative x plus 9. But if you write 9 minus x, you're fine. That's fine. Let me zoom in a little bit. To finish this off, I'm going to have to divide by 2. So let's rewrite what I have. 2y less than or equal to negative x plus 9. And we just got to divide by 2. Because we're trying to cancel out 2, that's getting multiplied to y, right? It's 2 times y. And the way to undo that would be the opposite of multiplication. Opposite of multiplication is division. So dividing by 2, We're going to do that to all of these parts as well. So we're going to have y less than or equal to negative 1 over 2x. If you're wondering where that comes from, it's negative 1x right there. So negative 1 divided by 2x plus 9 over 2, which I'm going to say is, I guess, 4.5. We can write it as 4.5. All right. There we go. So now we're going to graph it. So I'm going to let this x and this y, this is going to x represents, remember, cookies, and y represents brownies. I don't know how I can fit that on here, but we're going to try. Yeah, I got like lean sideways here. All right. And we'll let each tick mark be worth 1. So when you graph this line, we are going to start, I guess, at 4.5. So that'd be 1, 2, 3, 4, and 0.5 right there. That's my y-intercept. And then go down 1 and over 2. So we're going to go down 1, which is kind of like this half unit here, and over 2, which would be right here. Then we'll go down another 1, which would be right there, and then over 2, which would be here. Go down 1 again, and then over 2 again. That'll be right here. Go down 1 again, and over 2 again, and that'd be right there. Okay. So there's our line. Now, apologize for that. If you hear that, that's just the bell going off because it's at school, you know. I usually make these at home, but I got some time at school today. Anyway, now we're going to shade y is less than. Here's the important thing. It's the difference between this and a regular equation. Regular equation, we'd be done. We drew our line, we're good to go. But because we have inequality here, y is less than or equal to, we are going to shade the part below this line. Less than or equal to will be below the line, and if it were greater than or equal to, it would be above. That goes for regular less than and regular greater than as well. If it's less than, it's below. If it's greater than, it's above. So we would shade in this region right here. Now, what we're doing that for is we're indicating that we can, we don't have to use up 9 eggs exactly, right? We can make all the possibilities inside this region that I'm shading in. I can use up all those possibilities with 9 eggs. So for example, I can make 2 batches of cookies and 2 batches of brownies. You know, I don't have to use up all 9 eggs. If I did this, if I used 2 of each, right, that'd be 4 eggs for the brownies and then 2 eggs for the cookies. I'd use up 6 eggs. And that's totally fine. I have 9 eggs to do that. So everything within this shaded region is a possibility that I can make out of 9 eggs. I could make 0 and 0 if I wanted to. You know, I could make, for example, 4 batches of cookies. I should use a different color for this so it stands out. Choose blue. I could make 4 batches of cookies and 1 batch of brownies. I could make 3 batches of cookies, 2 batches of brownies. I can even get on the line right here, for example, and say, I'm going to make 3 batches of cookies and 3 batches of brownies, which is actually one that I mentioned we said earlier, right? So basically, anything that's on the line that I drew, that red line here that I'm overlapping in blue, anything that's on that line, I erased it, would use up exactly 9 eggs. Whereas everything below that line would use up less than 9 eggs, but that's okay. We can still do that. We don't have to use up all 9 eggs. And every ordered pair within that is a combination that we could theoretically make or bake. So why did we only graph in the first quadrant? So yeah, why don't we have any negatives here, basically? And that's a pretty simple question to answer. Don't have any negatives because can't make negative batches of cookies or negative batches of brownies. Can't make negative batches. Okay? I don't know if it's supposed to be ES or just S, but it's fine. All right. Number 2. Jesse's daughter went to Target and bought $1 or $2 items from the one spot area. I guess you guys know what they're talking about. The one spot area. You know, when you walk into Target, you know, immediately right by the cash registers, you got the little dollar section. It's got all the cheap stuff, like $1 or $2. That's where it's at. That's got the cool stuff there. Okay. Anyway, she wants to spend less than $20 at Target. List 3 possible combinations of 1 or 2 items she can buy. So, or $1 or $2 items she could buy. So, for example, she could buy, 5 $2 items and 3 $1 items. Now, this is not exactly $20, but it doesn't have to be, because she can go in and with her $20 buy those things. That would be $10, and this would be $3. Should be spending a total of $13, and there's nothing wrong with that. Okay. But if you want a combination that does use exactly 20, then maybe we can say 5 $2, 5 $2 items, and 10 $1 items, because that would be $10 here, and this would be $10 here, which would be $20 in total. Or just say maybe, I guess 4 $2 items and 6 $1 items. So that would be $14, but that's cool. All right, so there's just a couple possibilities. There's obviously a lot more, but that's just 3 that we came up with or we made up. Part B, write an inequality to represent the situation. So we're gonna have X be the $1 items and Y be the $2 items. So then it's 1x because it's $1 for those $1 items plus 2y, which is $2 for the $2 items. Now, I didn't want to say this, but I'm going to say it now. It says wants to spend less than $20. It doesn't say spend up to $20 or anything like that. It doesn't really give us a hint that we're including the 20. So actually, really, let's just go less than 20. Just kind of take this very literally. Now, if that's the case, this option right here that I said 5 $2 items and 10 $1 items, that would be actually wrong if we couldn't spend exactly $20. Maybe we want to change that to just 9 $1 items. So that would be less than $20. Anyway, I just wanted to point that out. It says spend less than $20. It doesn't say we can spend exactly 20. So we'll just keep it strictly less than. So now we need to graph this, right? So when we graph this, the first thing I'm going to do is try and rearrange this inequality. So I'm going to rewrite it here so I have a little more space. 1x plus 2y is less than 20. We're going to try and solve this for y. So we're going to subtract this x. 1x minus x is going to cancel out. We're going to have 2y equal to, again, this is on the right-hand side. You can read this as 20 minus x, or you can write it as negative x plus 20. As long as you kind of remember that it is a negative x, and then it is a positive 20, you should be good. So divide these by 2 to get rid of the 2 on the y. We're going to have y is equal to, or not equal to, I wrote equals to before I messed up. Less than, y is less than, negative 1/2 x plus 10. So now we're going to graph this inequality. Let's go over here. Does this go up to 10? 1, 2, 3, 4, 5, 6, 7, 8. No, it doesn't. Okay, so that's unfortunate. I guess we'll go by 2s, although that's kind of lame. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. I guess we'll go 14. Why not? All right. Don't need to go up that high, but we're all right. So the y-intercept, positive 10. So we're going to start with our first point at positive 10. That'll be that, which puts us right here. And then we're going to go down 1 over 2. So going down 1 is actually half a unit because remember we're going down by, each of these counts as 2. So I'm going to put these little dash marks here to keep up with the odd numbers between them. So down 1 over 2 would be right here. Down 1 over 2 would be right here. Down 1 over 2. Down 1 over 2. Down 1 over 2. Down 1 over 2. I'm just kind of continuing this pattern throughout. I actually ran out of room here. So I'm going to just, oops. Didn't mean to erase those. I'm going to actually extend this just a little bit. We're going to have 16 here, and we're going to have 18 here, and we're also going to have 20 here. That would be right there, and then right on that line. Okay. So Here's a very important point to make as we're doing this. So this is just less than. It's not less than or equal to. So remember how I mentioned in the first problem that when I draw a line here, that this is all the amounts that would equal exactly $20. If you go back up, I pointed at it earlier, that red line is exactly spending or using 9 eggs. So here in this case, this red line means using exactly $20. However, right, if we're just spending less than $20, we are not allowed to spend exactly $20. So how we're going to indicate that on our graph is we're going to draw that line as a dotted line instead of a solid line. What this dotted line indicates to us is that we can spend up to that line, but we can't actually include any of the points on that line. So for example, all these little dots that I drew, these little points that I placed, they're not actually going to be solutions to the system. They're only going to be kind of on the barrier, on the edge, because everything on this line would be exactly $20, but we're not allowed to spend exactly $20. We're only allowed to spend less than that. So the dotted line indicates to us that it's not equal to $20. Okay, now our y value is less than, right? If you look back at our inequality, y is less than that expression. So since it's less than, remember less than is below the line, so we would shade the region below the line. So it's going to be all of this right here, kind of similar to what we did in example 1 with the egg problem. Now, just a reminder, what that indicates to us is that any point, any ordered pair within that shaded region counts as a solution. So for example, I'll pick one right here. That is 6 $1 items and 4 $2 items. I can do that. I can buy that with my $20 bill or with less than $20. Any point within this region, it can be 10 $1 items and 2 $2 items. It could be 14 $1 items. Remember, the stuff down here at the bottom is our $1 items. This over here is our $2 items. So I could buy 14 $1 items, 2 $2 items, anything in the shaded region counts. Okay, even the little odd number pieces, like for example, 3 $2 items or 3 to $1 items and 5 $2 items. All those solutions work. Okay. So what's the difference between the ordered pairs that fall on the line and the ones that fall in the shaded region? So the ones on the line are equal, right? Okay, ones on the line are exactly $20, whereas ones below the line are below. I could say less than, but I like to keep that word going. Below the line is below $20. All right. Number 3. Oh, I gotta just use this. All right, number 3. Okay, there it goes. All right. The lacrosse team is raising money by selling cheesecakes. The players plan to sell an entire cheesecake for $24 each and slices of cheesecake for $3.50 each. If they want to raise at least $700, how many of each would they sell? Okay, so list the 3 possible combinations of entire cheesecakes and slices the players could sell to reach their goal. What I'm going to actually do is I'm going to answer this one last. This problem is a lot easier to do after I've already made my graph, because once I've made my graph, it's easy to just pick points like you saw me here. In that last problem, I was drawing those blue points left and right. I was able to find combinations anywhere on that graph. So once I have the graph drawn, it'll be very easy to identify those answers. So we're going to skip A and we're going to come back to it. So for part B, let's write an inequality that represents the situation. So we have $24 for entire cheesecakes. So we'll have X be equal to entire cheesecakes. Okay, and then Y will be the slices. So since an entire cheesecake is $24 each, we'll have 24x. That's $24 for each bit of entire cheesecake, And slices are $3.50 each, so it'd be $3.50 y to represent 350 per slice. Now we have to raise at least 700. So here's the difference between this problem and the last one. Here we want to make more than $700, right? We don't want to make less than 700. We want to make at least 700. So we want to make more than or equal to $700. Now I'm going to rewrite this because I kind of went over my graph a little bit. I'm going to need that space later. So it's 24x plus 350y is greater than or equal to 700. All right. Now graph the inequality and shade where the solutions are. So before I graph it, I'm going to solve this for y. Actually, do I want to do that? Yeah, why not? Okay. Well, all right. This one, I'm going to approach the graph a little differently here. Obviously, we can do it the same way we were doing it before where we solve for y. I wanted to do that for good practice because I know some of us, it's still kind of a struggle trying to solve for y, so it's good practice to kind of get used to it. However, there is another way you can graph these that you might find a little easier. And it's the extreme bounds is what I'll call it. I don't know if that's really a technical phrase for it, but that's what I'm going to call it. Basically, if the extreme bounds are how many entire cheesecakes could I buy and not buy any slices at all, right? Have y equals 0. Buy 0 slices and just buy all entire cheesecakes. Or the other way around, don't buy any entire cheesecakes and just buy a boatload of slices of cheesecake. What are those extremes? If I buy 0 of one and then a bunch of the other, right? How much would I need to make 700? So let's do that. So let's just pretend, let's say 24x. Let's cut out, let's say if y was 0, I'm not buying any slice. I'm just going to buy entire cheesecakes. I want to know when that makes $700. So that's what I'll do, right? I'll do 700 divided by 24, and I'll figure out what that extreme bound is. Oh. Give me a second while I get my calculator out. All right. 700 divided by 24, 29.16. Repeating. Okay. So that is entire cheesecakes. Okay. Now I'm going to come back to how I'm going to graph that later. All right. What if, let's not buy entire cheesecakes. Let's only buy slices of cheesecake. How many slices of cheesecake could I get and make $700? Ooh, not 70, 700. 700 divided by the 3.5 would be 200. Okay. Now here's the reason I did that, right? So I could buy basically 29 whole cheesecakes and no slices, or right as a max as a what's the word I just used? Like the far. Well, anyway, or I could buy 200 slices of cheesecake without buying any entire cheesecakes, which is kind of silly. But anyway, so what I'm doing here, x, y, x represents, I believe, entire cheesecakes, and y represents slices. I'm gonna go up by, let's see, I have to make this work up to 200. So if I do that, what if I go up by, can I make it, how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can make 10 work. So I'll say each spot here is 20. 20, 20. Oh, I got to go up 20. 20, 40, 60, 80, 100, 120, 140, 160, 180, and all the way up top, 200. Okay. And then I'll go, I guess, I want to spread it out a little bit. I only have to go up to 29 for this x-axis. The y-axis had to go up to 200, but the x-axis really only has to go up to about 30. So let's say I make it by 5. 5, 10, 15, 20, 25, 30. That's all. That's good enough for me. I'll add a little extra here just because, why not? But I don't need them. All right. So what I'm going to do is just plot the extremes. Y, the extreme is 200. 200 slices of cheesecake. I'm putting a point all the way up to 200. For the x, the extreme was 29.16. So I'll go pretty much 30, right? And I'll put a point there. And now, because a line is a line, it goes connecting 2 points. So without having to do like slope, rise over run, I'm just going to connect these two extremes. There we go. Okay. Now, remember our inequality, right? We have to make more than $700. So that line represents all the little order pairs, all the exact values of, getting exactly 700. Below the line would be making less than 700. Above the line would be making more than 700. Our goal is to make at least 700. So we want $700 or more. So we're going to shade a region above this. All right. Looks kind of terrible, but it works. So all the solutions are in the shaded region. Now let's go back to A real quick. A asked for, what are some possibilities that we could sell and reach our goal with? Well, let's look at all the shaded stuff all the shaded stuff, blah, blah, blah. Okay, 25. I'm gonna pick this point right here. That's 25 entire cheesecakes and 60 slices. If we sell that, then we're gonna make the amount of money we need. I'm not gonna pick anything too extreme. I'm not gonna go like way out here or anything. But let's pick some realistic ones, like right here. That is 15 entire cheesecakes and 120 slices. So I can do that. Or I'll pick this one up here. That's 10 entire cheesecakes and 160 slices. So any of those possibilities would make more than $700. What is the difference in the amount of money raised for ordered pairs falling on the line and the ones that fall in the shaded region? So again, it's kind of similar. On the line makes exactly $700. In the shaded region makes more than 700 doll hairs. What do the X and Y intercepts represent? So that's why I graphed it, right? I did this before even realizing this was even a question. So the X-intercept, in our case, X was for entire cheesecake. So X-intercept, which is right there at about 30. It's not 30, but it's like, it's pretty much 30, right? It's 29.16. X-intercept is max number of entire cheesecake to make $700 without selling any slices. The Y-intercept is the exact opposite. So the Y-intercept, which if we go back, was that 200. Our Y-axis represented slices, okay? So Y-intercept is max number of slices. Not entire cheesecake, but slices. To make $700 without selling any entire cheesecakes. Oh, doing so well. Okay. Oh, got sloppy there at the end, but it doesn't matter. It doesn't matter. All right. Okay, I'm gonna end this video here. If I want to do any more of these, I know I'm doing this before we're taking class, so I don't know where we stopped in class, but I know we didn't get further than that. So I might do the rest of these in another video. I might just assign them for homework, and we'll go over them in class. I don't know yet, but I'll figure that out. I will see you guys later this week.